Worked example 10, combination resistor DC circuits. Question 1. The four resistors are connected as shown above. Determine each of the following: the total circuit resistance, the supply current, the voltage drops over R1 and R2, the voltage drops over the parallel section R3 and R4. To get the total resistance of the circuit, the first thing I'm going to do is to simplify the parallel section with R3 and R4 in it down to a single resistance first of all. This will then let me add it to the remaining resistors in the circuit and get the total circuit resistance. It is going to be 1 over R3 plus 1 over R4, and if we then substitute those values in, we have 1 over 900 plus 1 over 1200, and that all simplifies down to 7 over 3600. However, that of course isn't the final total resistance of these two, because that 1 over R3 plus 4, we need to flip both sides in order to get R34 on top, so we can rewrite that as R plus 34 over 1 is going to be equal to 3600 over 7, and of course anything over 1 just becomes itself, so we can effectively ignore the 1, and that becomes 514.3 ohms of resistance. Now that we've worked out the resistance for R34, we can actually redraw the circuit in a bit of a simplified way: R1, R2 and R34. So this is now 510, 400 and 514.3. So we can now go ahead and say that the total resistance of the circuit is going to be R1 plus R2 plus R34, which is going to be 510 plus 400 plus 514.3. This gives us a total of 1424.3 ohms, or 1.42 kiloohms. Part B, work out the supply current of the circuit. Well, we have been given the supply voltage of 20 volts and we've got the total resistance now. So using Ohm's law rearranged, we can do 20 divided by our 1424.3, and this will give us a supply current of 0.014 amps, which we can then simplify down to 14 milliamps. In part C, we're asked to work out the voltage drop over resistor 1 and the voltage drop over resistor 2. So for both of these we can use the Ohm's law. So our supply current, because it's flowing through both resistors, IS times R1 and IS times R2. So in this case we have 0.014 multiplied by a resistance 1 of 510, and that gives us a voltage drop of 7.14 volts. And for V2, 0.014 times 400, which gives us a voltage drop of 5.6 volts. For part D, there are two ways we can go about it. We can work out the voltage drop using Ohm's law over the parallel section, in which we say, well, the supply current times the resistance 34 will give us the total voltage drop over that section. So 0.014 times 514.3, and that gives us 7.2 volts. Or we could do it using Kirchhoff's voltage law, which tells us that the total supply voltage is going to be equal to V1 plus V2 plus whatever voltage drop we get over 34 is. And so in that case we've got 20 equals V1, which we worked out as 7.14, plus V2, 5.6, plus our V34, means we can rearrange for V34 being equal to 20 minus 7.14 minus 5.6, which equals 7.26 volts. Now there is a slight difference in the answer there. That's okay, just with a different method, slightly different roundings and all that kind of stuff. we've ended up with a slightly different answer. But either way, absolutely, both are the same. Both give you the right answer. Question 2 of the worked examples. The 4 resistors are connected as shown above. Determine each of the following: the total circuit resistance for part A, for part B, the supply current, for part C, the voltage drop over R4, and for part D, the voltage drop over the parallel sections R1, 2 and 3. In order to start, just like in the previous question, we need to know what's in parallel and what bits are in series. To kick off the question, we need to identify which sections are in series and parallel with each other. When we've got 3 or more connections, as we do here and here, we can identify them as nodes. And then we can say, well, anything that connects from node 1 to 2 must be a branch. So we can highlight all the branches different colours. So we've got this branch here going from node 1 to node 2. We have a middle branch going from node 1 to node 2. We have our third branch going here from node 1 to node 2. And then of course we've got the overall branch going around the outside, through R4, through the cell, around and back to node 2. So there's the four branches here. Now remember, any branch that shares the same start and end node are connected in parallel. So you notice the red branch here shares the same start and finish node as the green and the blue branch. So these 3 branches, based on that definition, are in parallel. That means that we could treat these 3 as in parallel and then work out the resistance of them in parallel. 1 over R, in this case it's going to be 1, 2 and 3, is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. So we can go ahead and substitute our values in of 510 plus 1 over 400 plus 1 over 900. And when we get those 3 together and we add them up, we end up with, from the calculator, 341 over 61,200. And of course we need to again flip both sides in order to get our R123, which is equal to 61200 over 341, which equals 179.5 ohms. So what we've done is we've simplified these 3 parallel resistors into a single resistance. So that means we can re-sketch our diagram nice and simply, calling that R123 179.5 ohms and R4 1200 ohms in series with our battery down here. So that is the simplified version of our circuit, having simplified these 3 down into a single equivalent resistance of 179.5 ohms. We're not quite there for the total resistance, because now we need to add these 2 together to get the total resistance. So RT is going to become R123 plus R4, which is 179.5 plus 1200, which gives us a total circuit resistance of 1379.5 ohms, or simplified down to 1.38 kilo ohms. Part B asks us to determine the total supply current. Well, the total supply current, IS, is going to be our supply voltage, which we're given in the question. We're given in the question information up here. Is going to be our supply voltage, VS, divided by our resistance total, which we've just calculated, which becomes 12 divided by 1379.5. Again, just making note of the fact that I'm using the more accurate information here, keeping that as to give me the most accurate answer. So 12 over our resistance there ends up giving us 0.00869 amps. Converted into engineering notation, 123 ends up giving us 8.69 milliamps of current. In the book, I've rounded that up to 8.7 milliamps. Part C, we are asked to calculate the the voltage drop over R4. So V4 is going to be whatever current is flowing through I4 times R4. Looking at R4 here, it's going to be our supply current, IS, because R4 is connected in series with the battery, so whatever current is flowing through here, which is our supply current, must be what's flowing through R4. So I4 is going to be our supply current that we've just worked out in the previous step. So we're going to end up getting 0.00869 multiplied by R4 1200, which in this case ends up giving us a voltage drop of 10.44 volts. In part D, we're asked to determine the voltage drop over the parallel section 1, 2, 3. Or to do that, we can look at our diagram here. We have got a voltage drop over R4 here of 10.44 volts, and we've got a supply voltage of 12. So our remaining voltage drop is going to be 12, take away whatever we've got here, which is 10.44, and that'll leave us with our voltage drop over the parallel section. Our V123 is going to be our supply voltage minus V4, which in this case was 12, take away 10.44, which equals 1.56 volts over the parallel section. Question 3. The 4 resistors are as connected as shown above. Determine each of the following: the total circuit resistance, the supply current, the voltage drop over R1, the voltage drop over the parallel section R2, 3 and 4, the voltage drops over R2 and R4, and the current flow through each branch. We've got our battery coming into our R1 here of 2 kilo ohms. It then splits down to R3 of 4.2 kilo ohms, 2, 4 kilo ohms, and R4 of 3.5 kilo ohms. Again, just as we've done before, identify our points of 3 or more. So here's node 1, node 2, and then highlight our branches. So node 1 through this branch to node 2, and then we've got another branch from node 1 through these 2 resistors to node 2, and then lastly, in this case going from node 2 all the way around is our external branch here through the battery to node 1. So we've got our 3 branches, red, green and blue, and we can see that red and green go from nodes 1 to 2. They both share the same start and finish node, so that tells us straight off the bat that red and green are in parallel. Notice, however, on the green branch, R2 and R4 are on the same branch, one after the other, so these 2 resistors are in series with each other. And we need to simplify that down first, prior to then doing the parallel section, or treating the sections in parallel to get the resistance. So in order to do this, I'm going to start by working out the total resistance of the green branch, simplifying it, working out the parallel resistance of the green and red, simplifying it, and then finally working out the series resistance of R1 and this section here, and then simplifying it. R2 and 4 is going to be R2 plus R4, which equals 4,000 plus 3,500. So 567, so 7,500 ohms. And I'm now going to simplify that circuit down a little bit. So we've now got R3 and R2, 4. That's 7.5, and that's 4.2. And that's 2000. So now I've simplified this branch, this green branch, down to a single resistance. I can now simplify the parallel section again into a single resistance. So 1 over R3 to 4 is going to become 1 over R3 plus 1 over R2, 4. Which is 1 over 4,200 plus 1 over 7,500. 13 over 35,000, that simplifies down to 35,000 over 13, which then simplifies down to 2.7 kilo ohms or 2,000 700 ohms. So having now simplified down this combination section to a single resistance, we can redraw the simplified diagram where we've got R1, which is 2000 ohms, in series with R324, which is now 2700 ohms. And because these two are connected one after the other in series, we can now just go ahead and work out our total resistance for the circuit, which is R1 plus R324, which equals 2000 plus 2700, which is 4700 ohms total. And so that is our total resistance in series. In part B, we have to calculate the supply current, and in order to do that we're going to use Ohm's law rearranged, where we have the supply voltage divided by the resistance total, and in this case our supply voltage is 12 volts and the resistance total we just calculated is 4700 ohms, so that gives us a total supply current of 2.55 milliamps. In part C, we're asked to calculate the voltage drop over V1. So going back to our resistor here, we're basically looking for the voltage drop V1 across this resistor. So we've just calculated the supply current as 2.55 milliamps, and we know that R1 is connected in series with the source, so that basically tells us the current flowing through R1. So that means that to get the voltage drop for R1, we can just use V1 is equal to IS times R1, which is 2.55 times 10 to the minus 3, multiplied by the resistance of R1, which is 2000 ohms, and that ends up giving us a voltage drop of 5.11 volts. In part D, we're asked to calculate the voltage drop over the parallel section. So that is everything from here over to here, basically this whole section, this voltage drop here, VP, I'm going to call it V parallel. So the easiest way to know that is to simply say, well, my supply voltage is 12 volts and I'm dropping my 5.11 volts over here, so the remaining voltage drop is going to be whatever is left here. So to write that out fully, we could say that the supply voltage is equal to V1 plus Vp, so Vp is going to be equal to Vs minus V1, or 12 volts minus 5.11, which leaves us with 6.89 volts over the parallel section. In question E, we're asked to work out the voltage over R2 and R4, in other words V2 and V4, these sections here. So this is a slightly trickier one, where we're going to need to work out what our current flowing through this section is, and then once we know the current through this green branch, we can then work out the voltage drop over these two bits here. The alternative method is we use the voltage divider rule, where we say, right, well, if this is 4 kilo ohms and this is 3.5 kilo ohms, the total voltage drop over this section in parallel is going to be the 6.89 that we just calculated. So from there, we then can basically split the voltage over each bit. If we use the voltage divider rule, then we can say R2 over the total resistance for that section, which will be 2 and 4, multiplied by the voltage drop in that section across Vp, will give us our voltage over number 2. So that is going to become 4 kilo ohms over R4 plus 3.5 kilo ohms, multiplied by the total voltage drop in that section, 6.89, and that gives us 3.67 volts. And then to work out the voltage over V4, it's just going to be the voltage in the parallel section minus V2, which is 6.89 minus our 3.67, which equals 3.22 volts. So basically what we've done there is we've worked out the voltage drop over V2, and then knowing that the voltage drop over V4 must be whatever the total voltage drop over that section Vp is minus V2, leaves us with V4. That's let us work out our 3.22 volts there and there.